The vision of Pixel Photonics is to make everyone see the unseen. And we are doing this by providing the world-best photon detection platform that lives on a chip that enables you to see every single particle of light, our Arctic platform. Building the eyes for the quantum era means that we provide the detection needed for quantum computers, but also for quantum key distribution systems, where you have the information in single particles of light and photons, and in the end to detect this. Our Arctic platform differs tremendously from today's superconducting detectors by being integrated on a photonic integrated circuit.
For decades, photon detection has been an external component using fiber coupling to integrated chips. And for scaling such an architecture, this is not viable if you work with many thousands of optical modes. Integration is the only viable way forward.
Typical fiber-based detectors are not scalable enough to the numbers that are really needed for the quantum era. Just making fiber-coupled detectors better will not flip the script. Current detectors are coupled from the top, so the fiber is moving from the top, which means they can only be fabricated in small batches. They need to be hand-picked. You have semiconductor detectors that tap out typically around 25 to 30% efficiency in the near-infrared and are really noisy. And if you need better detectors, higher efficiency, lower dark counts, you go to superconducting detectors. But those are lab-grade equipment. They're quite expensive and not scalable. This is really something that is a dilemma for the quantum era, and we are solving this with our Arctic platform.
The community is moving towards integrated systems or chip-scale architectures, and the Arctic platform aligns exactly with this by making the detector an integral component of the design framework. In this way, the detector can be embedded directly into the design tools and be used as a component in innovative circuits. When the single-photon detector is no longer an external component, three transformational changes take place. First is scalability. A lot of components can be directly realized on chips. Second one is stability. Integrated detectors are inherently more stable and remove drift. And third, it's system-level innovation. Once the detector is embedded in the framework directly, an entirely new zoo of architectures becomes possible.
Putting our detectors as part of the Arctic platform on a photonic waveguide brings several advantages in terms of performance. First of all, it's polarization insensitive. It captures both polarities in the waveguide almost the same. Bringing the detectors on the waveguide allows us to make them shorter, which at the same time makes them faster, really absorbing 100% of the light. And this means the detectors are very fast and almost 100% efficient. Our technology is wafer scale applicable, so it can go on 8-inch wafers, and we can just fabricate those detectors in the hundreds or thousands. They are also less prone to fabrication imperfections because they are smaller. On the fabrication side, we can deploy full CMOS compatibility, so we can just put our detector layer on top of existing photonic foundry chips, then pattern these detectors also using CMOS compatible processes, and therefore it's really scalable. In the end, you can just print out wafer after wafer. Our Arctic platform can be used on basically any photonic foundry that has a front-end process that provides access to their waveguide, and this makes it very versatile. We can use this on US-based foundries, AIM Photonics, for example, and we did POCs here in Europe with Ligentech and also Lyonix. Our foundry-compatible back-end-of-line process goes in both of our current product lines. So the standalone systems, they can be deployed in any application where you already have light in fiber. Can be a quantum computer, can be a microscope, can be a light detection and ranging application. And the co-integration, which is directly on chip, is for really providing the scalability that is needed for huge systems towards thousands or even 10,000s of detectors.
Pixel Photonics technology removes the bottleneck of addressing each individual components. Single-photon detectors can be fabricated at scale, and a lot of devices can be embedded directly into the architecture. And this way, the detector is not an external backend, but it's really integrated into the computational framework. such a system on chip, I think that would be exactly what is needed for driving the community forward.
Success for Pixel Photonics is we provide the means to really make quantum computing fly, to really make it change the world and enable new modalities and applications in diagnostics and life science.